Functions. So how do we visualize functions and how do we define them mathematically? Functions are basically relations that take some values from a set like domain and map them to another element in another set, which in general includes more values, and we call them codomain. We have a specific definition for range, which is the output values of the function. From algebra, we know that a function like f from a set A to a set B is a relation with domain A and a codomain like B that satisfies the following two properties. First of all, for every element like x in the domain, there is an output value like y in set B such that the ordered pair x and y belongs to that relation that we denote by f. Second of all, for all elements like x in the first set and y and z in the second set, if x and y belongs to that relation and x and z belongs to that relation, for sure you can say that, hey, the output values are the same. Y and z must be the same thing. So basically, your function acts like a machine. You input some x values, and the output values are denoted by f of x. For example, think about squaring function. When you plug in some numbers, the function gonna take that number and raise it to the second power. If a and b are sets, and f is indeed a function from a to b, then given any element like x in set A, the unique element in B that is related to x by f is denoted by f of x. Basically, this is the output value of the function belongs to the range. So for example, if x is the domain of function f, including x sub 1 and x sub 2, and the function f map these two values to f of x1 and f of x2 in the codomain, and if you take these two output values, this is basically the range of this. Examples of functions and relations. Let A be the set including 2, 4, and 6, and B be the set including 1, 3, and 5. We're going to define three relations and we'll check to see which one is basically represents a function. The very first relation has the very first point 2 and 5, the second point 4 and 1, the third point 4 and 3, and the last point is 6 and 5. This relation is not a function. Why is that? You have 4 and 1, you have 4 and 3, but the output values are not the same. The ordered pairs 4 and 1 and 4 and 3 have the same first element, but different second elements. Take a look at the arrow diagram. This relation maps 2 to 5, 4 to 1, 4 to 3. So this is the problematic issue here. This doesn't satisfy the definition of a function. There are two arrows coming from one single value in the domain, and you have two different output values. One points to 1, and the other one points to 3. Let's go back to these two sets, and then define another relation like this. X and Y belongs to Cartesian product of A and B. X and Y is in relation S if and only if it means that Y is equal to X plus 1. Is this a function? Well, if you look at Y equals to X plus 1, You might say, hey, it must be a function because I saw this in algebra. But the algebra has different domain than the domain and output belongs to B, which is 1, 3, and 5. So is this a function? This is not a function. Why is that? If you take, for example, 2 and plug that into this relation, y becomes 2 plus 1 or 3. Okay, 3 is just right here. What if I plug in 4? If I plug in 4 here, I get the output value to be 5, which is just right here. But if I plug in 6 from the domain, the output value must be 7, but I don't have any 7 belong to the set B. So it means that one output value is missing. So this cannot be a function. You have some input values and the output values are not there. So 2 maps to 3. If I plug in 2 here, 2 plus 1 becomes 3, which is just right here. If I plug in 4, I get 4 plus 1, which is 5, which is just right here. But what about 6? If I plug in 6, 6 plus 1 is 7, which doesn't belong to set B. So this is not a function. Let's take a look at another relation. Relation T is defined by an arrow diagram like this. This relation maps 2 to 5, maps 4 to 1, maps 6 to 1 as well. It's not that you have an extra value in B, which is fine. You don't have any issue with having an arrow values in the second set. T indeed is a function. Each element in the domain is related to some element in the codomain. The range of this function is 1 and 5. Both properties for the definition of a function are met here. So basically you have a function. So every function indeed is a relation, but not all relations are functions. Let us go back to the definition of Cartesian product between two sets. We define a relation like C. If and only if you square x and y, the summation must be equals to 1. As you remember, this is the definition of a unit circle. For a unit circle, it doesn't pass vertical line test. If you have a vertical line, then the vertical line has more than one intersection with the graph. So this doesn't represent a function. This is basically just a relation. Observe that there are many real numbers like x and y that are not in C. We only accept x and y's that if you square them and add them together, it is equal to 1. All the points on the unit circle. But again, for example, if you take a half and a half, the output values are going to be different. So it means that this is not a function. This is just a relation. So let us move on to official definition and talk about pre-image. A function like f from a set like x to a set like y, which is denoted by f that maps x to y, is indeed a relation from x that we call the domain to the second set that we call the codomain that satisfies two properties. First of all, every element in the domain is related to some element in the codomain. And number two, no element in the domain is related to more than one element in the codomain. So given any element like x in the domain, there is a unique element in y that is related to x by f. if we call this element like y, then we say that f sends or map x to y, or f maps x to y. We write it this way: x is mapped to y by f, or f maps x to y. The unique element to which f sends x is denoted by f of x, and as you remember, we read it as f of x, or the output value of f, or the input value of x, or the value of f at x, or the image of x under f. So we have different way representing f of x. F of x, the output of f, the value of f, and the image of x under f. The set of all values of f taken together is called the range of f, or the image of x. So range of f, or the image of x under function f. Symbolically, we write down the range of f, or the image of x under f, as the set of all output values such that those output values are connected to x by f. So we can visualize it this way. This is the domain, and you have, for example, some values in the domain. Those are mapped to some y values in the larger set or codomain, and this smaller set is called the range of the function, or the image of x under f. Given an element like y in the second set, there may exist elements in x with y as their image. If f of x is equal to y, then x is called a pre-image of y, or an inverse image of y. The set of all inverse images of y is called the inverse image of single value y in the second set. Symbolically, we write it this way: the inverse image of y is the set of all elements in the domain such that f of x is equal to y. Usually, suppose you have the domain and you have codomain. You take an element in the domain like A and you map it to f of A that you call B. This belongs to the codomain. This is basically the image of A, which here we represent by B, and it belongs to the codomain here. The inverse image of Y is the set of all x values here that f of x is equal to y. So if I take a y here, we're looking for some x values in the codomain that f of x is equal to y. So this is the way that we define a function. It needs to satisfy two important properties. Let's go over a few examples. Recall that if x and y are finite sets, you can define a function like f from x to y by drawing an arrow diagram. You make a list of elements in x and a list of elements in y, and draw an arrow from each element in x to the corresponding element in y. Let's take a look at the figure here. The domain includes x sub 1, x sub 2, x sub 3, x sub 4, and this function maps these to some output values in the codomain. The range only includes y1, y3, y4. This arrow diagram define a function. You can check these two conditions yourself. Basically, every element in the domain is mapped to some elements in the codomain. Also, no element in X is related to more than one element in Y, right? X1 is mapped to Y3, X2 is mapped to Y1, X3 is mapped to Y3, and X4 is mapped to Y4. So we have a function presented here. These are simple functions in discrete math. In calculus, you learn about continuous functions as well. Question says, which of the arrow diagram in the figure define functions? Your X or the domain is defined A, B, and C. Y only has 4 members, 1, 2, 3, and 4. So this relation maps A to 1, B to nothing, and C to 3. This is not a function. It doesn't satisfy the very first condition. You have an element B in the domain that is not mapped to anything. So the first condition is not met. This is not a function. This is just a relation. Take a look at the second diagram. A is mapped to 1, B is mapped to 2, C is mapped to 2, but C is mapped to 3. So here you have C, which is mapped to 2 different output values. This is not a function. Let's take a look at the third diagram. A is mapped to 3, B is mapped to 1, C is mapped to 3, and all conditions are met here. This is indeed a function. Let X be A, B, C, and Y be 1, 2, 3, 4. Define a function f from X to Y by the arrow diagram below. F maps A to 2, B to 4, and C to 2. Question says, write the domain and codomain of this function. Well, obviously, the domain is set X, including A, B, C. Codomain includes set Y, 1, 2, 3, 4. You're going to list them all. Question says, find f of A, f of B, and f of C. So if I plug in A into this function, what's the output value? The output value for f of A is 2. The output value for B is 4. The output value for C is 2. C, what is the range of the function? Guys, range and codomain are not necessarily the same thing. Range is a subset of the codomain. Range only includes 2 and 4. It only has 2 members. So again, the range is the subset of the codomain all the time. It's not necessarily the same set, it's the subset. Let's go back to the question and find the answer to the following question. Is C an inverse image of 2? Is B an inverse image of 3? So C is an inverse image of 2, all right? Take a look at 2. 2 is mapped backward to C because f of C is equal to 2. But take a look at 3. 3 is not mapped to anything. So B is not an inverse image of 3 because 3 is not mapped to anything. Question says, find the inverse image of 2 and 4 and 1. Okay, the inverse image of 2 includes 2 elements because 2 is mapped to 1 and also mapped to C. So 2 is mapped to A and C. 1 doesn't map to anything. 3 doesn't map to anything. 4 is mapped to B. So the inverse image of 2 includes 2 members, A and C. The inverse image of 4 is going to be set including B, and the inverse image of 1 is empty set. So inverse image of 1 is empty set, is not mapped to anything. Let us represent the function as a set of ordered pairs. In that case, f, the function, can be represented as a comma 2, b comma 4, and c comma 3. This is an ordered set of ordered pairs representing this function in set notation. Theorem, a test for function equality. If f maps x to y and g maps x to y, both of them are functions, then the relations are equal to each other if and only if the output values are the same. So please note that for these two functions, the domains are the same. We're going to say that, hey, relation-wise, they are equal. This means that the set of ordered pairs are equal to each other if and only if the output values are the same. Let's take a look at the proof. Suppose f and g are functions. It means that f and g are relations that satisfying those two conditions that we impose for functions. F and g are subsets of the Cartesian product between x and y. There is no doubt there. And for an ordered pair like x and y to be in relation f, it means that y is a unique element related to x by f. So we can denote y by f of x. With the same argument, for the ordered pair x and y to be in G, it means that y is the unique element related to x by G. So y is also equal to G of x. Now, suppose that f and g are equal to each other. Since f and g are equal to each other, then if x is any element of the domain x, for x and y to be f, it means that y is equal to f of x. But since f of x and g of x are equal to each other, y is equal to g of x. But what's the meaning of this definition? It means that x and y is an ordered pair in G. So any ordered pair in F is an ordered pair in G. It means that F and G as sets of ordered pairs are the same. Conversely, if F and G are equal to each other as sets of ordered pairs, it means that for every x in the domain x, y is equal to f of x. If you plug in x into f, you're going to get some output values like y. It means that the ordered pair like x and y belongs to this set f. But at the same time, we know that f and g are the same. So whatever you take from f is going to be in G. But x and y in G means that y is equal to G of x. So y is equal to f of x, y is equal to G of x. It means that since both f of x and G of x equal to y, f of x and G of x are the same. The output values must be the same as well. So when you have theorems like this, including if and only if, you need to start from one side and go to the next side and prove both of them. So here, the conversely part means that, hey, now we assume f is equal to g, and then we prove that f of x is equal to g of x. Example for you, let G sub 3 be the set including 0, 1, and 2. We're going to define functions f and g from J3 to J3. For example, function f is defined as x cubed plus x, x squared plus x plus 1 mod 3, and g of x is defined as x plus 2 to power 2 mod 3. We want to know if f and g are equal to each other or not. Let's take a look at the table below. Set x to be 0. When x is equal to 0, x squared plus x plus 1 becomes 1. This is 0, this is 0, so the output value is equal to 1. Now, x squared plus x plus 1 mod 3, 1 mod 3 is 1. Now, if you calculate x plus 2 to power 2, it is 4. So, x plus 2 to power 2 mod 3 result in 1. 4 mod 3 is 1. So, as you can see, you have the same output values. You can plug in other values like 1 and 2 for x. Calculate your x squared plus x plus 1, and then f of x, which is x squared plus x plus 1 mod 3. You're going to get 0 and 1. If you do the same thing for function g, you're going to get the exact same output values, 0, 0, 1, and 1. So that's why you say that, hey, f and g are equal to each other. The output values are the same. The domains are the same. So basically, you have equality between two functions.